All right, the next thing to discuss is some properties of these integral signs. We actually already learned some of them. So when you're doing antiderivatives, the symbol is the same, so some of the things are going to still apply. If we add or subtract, we can split up our integral into two different parts. So we did that with antiderivatives, kind of break up things. We also had, if we have a constant multiple in the inside, we can bring it out in front. So those two things we've already used with antiderivatives when we're using this curly S notation. But the fact that we add these A's and B's, these endpoints, doesn't change the fact that these two things are still true. But there are some new rules now that we're thinking about. This is the area under a curve between 2 points. If I use the same endpoints, so there's not going to be any width between A and A, so it's width 0, so we always get 0. So if I find the integral from one number to itself, there's no width to that area, so it's always just 0. This one might be a little bit weird, but if I take my two values and I switch them, so now B is on the bottom, A is on the top, we just make that a negative area. So we're kind of going backwards along our function. We're doing something in the opposite order. It makes sense to make it negative. So we just flip the two kind of endpoints. We get the same answer just with a negative sign. And the last one will end up being one of the most useful ones. If we have A and B, so we're trying to find the area from A to B. If we can find some area or some place C in the middle, instead of finding one big area from A to B, I can break it up into the A to C part. So that would be that integral, and then the C to B part, which would be that integral. And it seems pretty obvious that you can kind of cut this in the middle. You never know with math that something that seems obvious is actually going to be true, but in this case it is. If you find a middle point between A and B, you can break up your integrals into multiple parts. And why would you want to do that? Well, there's this thing called total unsigned area. So in our normal, just so we just put the integral sign, there will be negative areas and positive areas. But in some cases, we only want to make all the areas positive. So if we were to do this similar problem to what we did before, we have the graph of x, which is just our diagonal line. And we're going to find the area from -2 to 4. If we just use our integral notation, we get some negative area down here and some positive area up there. But that isn't what we want. In this case, we want total unsigned area, so we don't have any negative answers. So then we would have, this would be the integral from -2 to 0 of x dx plus the integral from 0 to 4 of x dx. But we know this left-hand one would be negative because it's below the x-axis, so we're just going to put an extra negative sign there. Another thing you could do is you could do from 0 to -2. That also kind of puts an extra negative sign. But the basic idea is unsigned area. We don't get any negative numbers, so this is area 2. This is area 8. So my final answer, the total unsigned area is 10. If we let them cancel out, we got 6 when we did this example. But with unsigned area, we just get no negative numbers and we get 10. There's not really a notation for unsigned area, so you just have to write it in words. But this integral, you'll have negative values. So if you say unsigned area, you can't really use the integral notation because that'll give you some negative areas that you don't want.